and our kind of journey in adopting Hadoop and Spark, and how we've tried to really leverage the best aspects of Spark into our architecture in an industrial environment. So early on in my career, I started out in machine learning. Back then it was called neural networks, now it's kind of shifting back into that. Looking at diagnostics for human diseases and trying to do early detection. And next phase was at Teradata, applying kind of early big data analytics. Teradata was a pioneer in parallel shared nothing data warehouses. A little bit more expensive, and I think it's been great to see the Hadoop ecosystem really flourish and extend that reach to other domains that maybe were not as applicable for a system like Teradata. And so after a number of years at Teradata, I broke into the industrial realm and consulted for a number of years in oil and gas and power, doing kind of reporting and optimization solutions, and ended up meeting my co-founder. And what we were working on was technology to predict and prevent equipment failure, so basically stop machines from breaking. And does anyone remember this particular event? So April 2010, the Deepwater Horizon, basically the blowout preventer failed to shear the rams, and there was a natural gas explosion which killed the 11 first responders on that rig, where when everyone else was evacuating, they had to go and try to stop things. And big tragedy, but I think for us it was kind of a watershed moment, because it really showed the gravity of the situation in the industrial IoT, asset-intensive industries. And you know, when you go on these environments, I've been on a drilling rig, and you look at the challenges these people are facing. These are a lot of very, well-educated process and reliability engineers, and very challenging environment where we were looking at what technologies can we apply to try to prevent these kinds of catastrophes. So really what we've been trying to build is this system to enable smart machines. And there's two perspectives on that. One aspect is what we call predictive. So kind of if we detect a problem, what's our time to act? Is it 30 days, is it a year? And the second aspect is what we call prescriptive, which is what do you need to do? What's the prescription? What's the intervention? And really both are important when you're talking about dealing with these kind of situations. And I think one kind of analogy is, imagine if you went to your doctor and he told you, you've got a year to live unless you change something, but he couldn't tell you what to change. It wouldn't necessarily be that useful. So you really kind of need both of those perspectives. So I'm going to show a quick video clip here, and we'll see if the audio will come through.
So they can tell you they need attention before failure causes disruption, losses, safety issues, and environmental incidents. We've mastered the art of prescriptive maintenance for big data and industrial machine learning by harnessing conscious monitoring agents that perform tasks impossible for experts to do. Conscious monitoring agents interpret every failure signal, every minute of the day, and provide insight to when a failure will occur, how it will happen, and how to avoid it. Our software is heavily used in asset-intensive industries, such as oil and gas, power and energy, mining, transportation, and pharmaceuticals, where the consequence of failures can be costly. Mtell smart machines are effective because they directly ask the maintenance department for assistance, but only when assistance is necessary. This means dramatically
So I'll skip some of the marketing aspects, but this is kind of some of the background, and I'm going to talk about what we call machine learning agents today. So agents are entities that are looking for a symptom, and they have a certain amount of prescriptive information attached to them, kind of in terms of guidance and work process. And so that's going to be a key term we'll explain when we talk about kind of operationalizing this from an IoT perspective. So kind of zooming out for the IoT, we're talking about collections of sensor networks. Really connecting sensors to the internet was a first stepping stone, but now with the cheaper big data solutions, we're finally able to amass enough data to approach some of these kinds of challenges and address them on a broad scale. And of course also the cloud computing and developments in analytics have been really important. And looking at the industrial IoT, looking ahead to 2020, which is only 4 years away, You're talking about 4 billion connected people, about 25 million apps, 25 billion connected devices, some of them intelligent with some embedded information, and 50 trillion gigabytes of data. So really not too far away, and some interesting things happening there. So for use cases, there's a whole really broad variety of horizontal use cases in IoT and in industrial IoT. Some of the ones we're going to focus on today: condition monitoring, really just monitoring machines, remote monitoring. So that's been a key evolution where now that you've got all these remote plants, maybe networked, whether you have a central data center or you're using a cloud solution, you can now have a small group of subject matter experts remotely administer a lot of these facilities. So it could be a mine, it could be a fleet of refineries, could be a fleet of locomotives. But now we're enabling small groups of SMEs instead of having to have all these people at each individual facility. And shared learning is another key opportunity that with aggregating multi-site data, we can do multi-site analytics and look at transferring learning from individual machines across those boundaries and actually across site boundaries as well. So that's one of the things we call transfer learning. So two of the real data sources we had to tap into to look at this kind of IoT solution, we have streams of sensor data, so all the instrumentation we're putting on equipment, and we're also getting maintenance history. So it's like you go into your doctor, you get an EKG, but you also have a medical file of all your history of incidents you might have had, and we really have to correlate those two to get a complete picture of the health of these machines. And we had to apply some techniques to be able to correlate those two. And maintenance is kind of like event. We get the physical asset hierarchy of an industrial facility, but we also get the maintenance history, which we can mine for potential breakdowns or unplanned maintenance. And then what we want to do is learn signatures that led up to that and learn how to intervene. So some of the data aspects, down at the raw data realm, we have, of course, sensor data, maintenance work orders, a variety of type of operational event systems. Above that, we apply some different open standards at kind of the metadata level. So we adopted a standard called Mimosa. There's ISO 14224. We also templatize sensor information to help kind of span that across fleets of machines. Then above that, we have kind of some benchmarking and statistical information about mean time between failures, mean time between repair. And at the very top, we focus on building out libraries of useful information, including machine learning agents, as well as other types of preventive maintenance plans and prescriptive plans to tie to those. So to use another human analogy, when we first started trying to attempt transfer learning across machines, we ran into some challenges where certain machines are different. They might both be an electric submersible pump, but they really have different characteristics. And so the question became, how do we figure out what's important to kind of know which machines are similar and which machines are different? And so we started working on a project of centralizing a taxonomy, which we called the Machine Genome Project, of what's the important, of course, the make and model, the type, but what other contextual kind of operating context information are important from an analytics perspective. So what's kind of the metadata we need to segregate subpopulations to apply our analytics to? And again, this movement from what we call tier 1, which is at a site or industrial facility, to tier 2, which is cloud or central data center, kind of private cloud, has been a key shift from a technology perspective and leading us into the big data territory. So quick question, can anyone recognize what this image is?
My lunch?
What's that? It's okay, so the city's Los Angeles, but what about the thing on top of it? Comet, very good. So that's Comet 67P, which the European Space Agency landed a probe on not too long ago, and it's just kind of a visual representation of big data, I guess, in this case. But in the industrial realms, a typical drilling rig can collect a little over 300 billion measurement points or readings per year. So when you look at a fleet of rigs, you get into the 30 trillions, and then across 10 years, the numbers get very big. So it lands us kind of squarely in the big data territory. So we started building out the big data solution to store this data, and we adopted a solution called OpenTSDB that sits on top of HBase, which is the columnar database, or MapRM7 tables, which is another optimized version. So what we liked about OpenTSDB is it's a sorted row key system, and they put some of the timestamp into the row key so that you can do efficient queries by date range for sensors. And so for us, that was a very efficient data model for data access, and we built kind of our tag namespace and data IO management on top of that layer. But we ran into the next challenge, which is, okay, we have 20 terabytes of history or 200 terabytes of history. How do we load it into these Hadoop clusters, using an OpenTSDB compatible model? It turned out while it was very efficient at query, it was not very efficient at ingestion. So we actually worked with MapR, and the MapR team went and did a lot of optimizations, actually got a 100x improvement on the ingestion, did a benchmark on a 10-node cluster achieving 100 million data points per second ingestion, which was state of the art in the industry. So we were very excited about that, and it finally solved the feeding the beast challenge that we were having with some of these larger deployments. And basically what they did is, they batched inserts into blob collections that could be put in as one insert instead of all these kind of chatty inserts. So now kind of moving on to the analytics, which will take us into the Spark aspect. We talk about descriptive, looking backwards about what happened, predictive, trying to look at prediction horizons about what will happen, and prescriptive about interventions. So Gartner kind of did a matrix view of this about descriptive, and they also had a diagnostic, kind of looking backwards, but trying to do root cause profiling about why certain things happened, all the way down to prescriptive, really looking at solutions that add the decision support to walk analysts or maintenance planners through that process. So now we're going to talk about these agents. I've used that word a couple of times. For us, a machine learning agent is an entity looking for a specific pattern, but also attached to decision support information and prescriptive actions to take when that symptom is detected. And so we have 3 different types. You saw a couple of them in the video. Hidden failures, looking backwards and finding unlabeled events, which could be process upsets, it could be unlabeled breakdowns, but looking backward to identify those to basically to improve our analytics. Anomaly detectors and failure agents are forward-looking agents. So these are the ones we actually deploy. Anomalies just look for unknowns, things we've never seen before. We don't know really what it is. We try to help investigate, but it's an unknown. And failure agents look for recurrences of known signatures or patterns. So those are failure agents are what get in the prescriptive aspect. So when you're monitoring a machine, you'll typically have 1 or more anomaly detectors and then a series of failure agents looking at very specific events. So patterns of bearing failures, when it trips, you replace a bearing, impeller failures, drive coupling failures, etc. So agents, one of the key things, this industry, there's a lot of some older engineers that are getting close to retirement age. So there's a definite knowledge gap coming up. So anything that can help kind of do knowledge capture, knowledge retention is really important. And of course, these agents are a framework to do that, and also to learn really precise patterns that probably a human wouldn't be able to identify in the first place, but attach that to the prescriptive part, which is where humans come in, where they need to intervene and perform that maintenance. So has anyone heard of the PF interval in reliability engineering? Oh, we have one, very good. So can you define what the P would be? Okay, oh, very cool. Well, P, and there's different definitions, sometimes depending who you ask, but F is a failure point, and P is the earliest detectable degradation leading up to the failure. So the word detectable is kind of an interesting term because as technology improves, it can move farther and farther out in terms of what you can detect. And so of course with our multivariate machine learning, pattern recognition, we're trying to move that farther and farther out for early warning. So now let's get into kind of the platform aspect and the Spark and some of the solution components to make this come together. So we have our equipment information, and we can pull a lot of that out of these asset management systems, the hierarchy of assets for each facility. We model the mapping between sensors and physical assets. So you might have a compressor, how many sensors does it have? What are the subcomponents attached to it, motors and pumps, etc. What are those mappings? And then we templatize the sensors into what we call sensor templates. And that's the underpinning of looking at transfer learning across individual machine, or in the example, compressor boundaries. A key thing where, when we talk about operationalizing, is what we call live agents. So really, looking backward, doing analysis, there's tons of tools to do that. When you want to deploy live agents and do governance around that, trigger alerts, make sure alerts are acted upon in terms of prescriptive action, priority escalation, just all the requirements for a real kind of operations center to take action on these kinds of things is what we call really operationalizing. And then of course some of the analytics part as far as machine to machine, transfer learning, and some capabilities that tie into performance, usage, wear, fatigue, etc. So more traditional type benchmarking information. So those are all some of the key things that there's a lot of different solutions that touch on different aspects of that, but those are kind of a broad picture of the things that come into play. So, when you're approaching analytics in this realm with temporal kind of pattern recognition, part of it is signal processing. So taking all these signals, cleansing it, doing derived feature extraction, kind of auditing and detecting sensor quality issues, doing interpolation. We tie that into an equipment taxonomy. And it's interesting in the industrial realm, there's several different open standards that all kind of compete, as you see in a lot of standards movements, but they all kind of have interesting bits and pieces of what we saw as an overall solution. But it's important to try to do that to templatize your equipment from a metadata perspective. Then you apply your analytics. So you want to make sure you've built things up very carefully by the time you start doing your machine learning. You're doing things on a proper foundation of metadata. And then there's different aspects that get into more when you now have fleets of equipment and facilities, an operations center where people can respond to alerts in the field, do investigations, integrate with maintenance management systems. So those are some of the other kind of functions there. So transfer learning, we'll talk a little about. I'm actually going to show a video that explains a little bit of how we do this, in particular in oil and gas as an example. So let's see if this will come through here.
Mtell smart machines are constantly updating and expanding their knowledge base by sharing learned behaviors. Smart agents automatically share new behaviors between machines within a plant or facility once they have been learned. After a short retraining period, every machine is equipped with the same safety and breakdown protection. Sharing is also not limited to a single location. Smart agents share behaviors between facilities as well as machines. This process, called transfer learning, improves throughput and provides state-of-the-art safety and risk management to multiple locations. Our smart agents form a network that universally communicates all known conditions for improved equipment protection globally.
And so when we started down this path, we actually had to work on more of a peer-to-peer model, but the nice thing with this whole evolution with big data and cloud has been that a lot of it is now centralized, so we're able to just do the transfer learning at tier 2 instead of worrying about peer-to-peer connections between drilling rigs and facilities and so on. So really what we quickly encountered was a huge problem, which was now that we're dealing with tens or hundreds of billions of points and we're trying to train machine learning models on these, you run into a massive memory and compute challenge, which is well beyond the capacity of a single server. And so we were looking around, and around that time Spark really started to mature and gain momentum. And so we looked at what's the way we can adopt that, tie that into our work with OpenTSDB and Hadoop, and operationalize it into a kind of a platform approach. And so, of course, the key thing was loading data into RDDs, or resilient distributed data sets, as kind of a hot storage mechanism. So machine learning is a very iterative process where it's going to churn through a data set, maybe tens or hundreds of thousands of times as a process of learning, often using learning algorithms like stochastic gradient descent. So you need kind of a hot memory repository to churn through that. And so Spark was really a perfect fit. And then leveraging OpenTSDB and MapR in this case for kind of the cold storage to keep all the history. So the RDD, of course, read-only collection partition can be rebuilt so it's robust. And really for iterative tasks, as you'd expect, it's much faster for in-memory calculations. So it's kind of combining big memory with big data as kind of a combined approach there. So in terms of our Spark integration, we had our own machine learning library initially, and we still do, but we're seeing so many machine learning libraries coming out. You got Google TensorFlow, Azure Machine Learning, a variety of third-party ones that some of which integrate into Spark, some of which are standalone. So we've really mainly looked at the ones that tie into Spark, but we're also working with Google TensorFlow. But the key thing with Spark is that it plugs right into the distributed memory kind of RDD framework. So these libraries are built now to be able to cluster machine learning in a distributed horizontal fashion. So, because it is beyond the ability of a single server node to process. So that was very useful. So Mtell kind of fits in. We built a REST API to basically wrap the Spark cluster and interface in. We also have a REST API to talk to Spark and also to talk to other third-party machine learning systems in general. So I'll actually show you a quick example of the API that we've built out. So basically, managing agents, the challenge we initially encountered was we want to tie into Spark, but we had to build a bridge between Spark hosted machine learning agents to talk to OpenTSDB, so kind of transfer the cold data to hot data to big memory and then go through a training process. So we built out a system to do that, and part of the metadata that we exchange when we go to train an agent, for example, we'll pass in all the required sensors, the date ranges of data to extract, and information how to kind of combine that into sort of a data frame that can then be used to train different types of machine learning models. So these are some of the methods. We have some that support TSDB. We also made methods that basically you can just pass in the data. So you can either pass it in or you can kind of pass pointers to OpenTSDB and it will go out, get the data, bring it back in. So, yeah, so just quickly, we talked about the TSDB aspect, the RDD data frames, the REST API, etc. So that's kind of opening up our system to talk to more third-party systems and be more plug and play, which I think in the machine learning realm, there's kind of a battle now for who will have the key machine learning library everyone will use. So everyone's kind of open sourcing from Facebook to Microsoft to Google. We're kind of remaining Switzerland because they all have different pros and cons so far from what we see, but there's big companies working on them, so I'm sure one will probably emerge, but in the meantime, we'll just support whatever that fits the opportunity the best. So one key thing with further operationalizing a system like this is the industrial realm is never static, so you need a system that can adapt and manage to change. And so machine learning inherently is a learning system from that perspective, but you have to build an infrastructure about when to retrain, when to recalibrate. And so one of the things that we did is we have a feedback loop. And so if we trip, and if a failure agent trips for a known recurrence of a signature, okay, we've seen it before, very accurate. We typically trip an alert, they go and do an intervention, do a repair, and that's all that needs to be done. But when we trip an anomaly, it's a little bit more of an unknown. So we send an alert out, maybe they do an inspection, maybe it's a new operating state, so it's an unknown, but it's a new normal unknown. And so now it's a known. So what we want to do is retrain or recalibrate our agent with that new sensor data. So that's part of that feedback loop that comes in. But maybe they do an inspection and determine, you know what, that bearing was starting to degrade in a way we've never seen it before. Now we actually generate a failure agent label it, so now it has the prescriptive information. And now we can also get typically a greater kind of lead time with that approach.
So how often do you retrain your models, right? Because this is going into more ground truth to retrain your model, right? That's the end result of that. That's a
Yeah, it'll typically retrain. In some cases it can recalibrate using a different technique, but usually it's retraining the model with the new data.
and that's every day, week, month.
It's event-based,
Okay.
so it's kind of managed by exception. The longer you have data and the longer it's been running, the less it's probably going to happen. So, yeah, it kind of depends.
Okay.
So yeah, just kind of recapping predictive prescriptive analytics, some of the goals, obviously increasing output cost, but I think a big thing is hopefully preventing some of the environmental catastrophes we've seen. I think it's a very tough environment in industrial, and there's very smart people working there, but they have a very difficult job. So we're trying to find ways just to give them more insights and information, leverage all the data they've been collecting. So thank you for your time. I guess we'll stop. Do we have time for questions or? No? Okay.
Thank you. That was a fantastic talk. Thank you, Alex. And I feel fortunate having been able to see that, because his use case that he talked about was actually a use case I worked on. So really awesome stuff. I just want to give a quick reminder, the survey, at the end, we'll put the slide back up that has the link to the survey, but the survey will also go out in an email afterward.